Well, good afternoon, everybody. Welcome to the final day of our virtual Northern Landscapes Festival. My name is Jessa Frost. I am the program director here at North House Folk School, although here at North House Folk School these days means here at the home office at my home in Tofty. But it is a real delight to welcome so many of you. It looks like almost 100 people have joined us to learn from one of our favorite instructors about a topic that has a long history, right? And I should note is a class that's often hard to get into. So this is a great way to connect folks. If this is your first time joining us, North House Folk School is located in Grand Marais, Minnesota, right on the shore of Lake Superior. And typically we welcome about 3,000 people from all over the US and beyond to our campus to learn about geology and to learn about how to make their own mucklucks and timber framing and shoe making and wood-fired oven construction and baking, you name it. We teach a really wide variety of traditional Northern crafts. During the current pandemic, bringing people from all over the United States into a room to learn from one another has gotten a lot more complicated. And so we have moved much of our programming online. We are offering a series called Crafting in Place that has all kinds of different videos and webinars to help you, our community, stay connected with one another and with our instructors, and hopefully to provide some much needed inspiration and connection in the world. So that's what we're trying to do, and we hope it works. Let me tell you a little bit about how Zoom works if you haven't been on a Zoom webinar before. You are able to ask some questions, and I see somebody, Wendy, has already raised her hand. If you would like to ask a question during the presentation, we'll be answering them primarily at the end. So, but you can submit a question at any time that it occurs to you. And the way that that works is if you hover over the bottom of your screen, you should have an option pop up that says Q&A. And that would be a great place to put your question in, and then we will address it when we get to the end of the talk. You can also raise your hand. We will, once we get through the questions in the Q&A box, we'll answer those questions. And by allowing you to speak, we'll unmute you and you'll be able to ask your question in person. Sort of. And otherwise, if there's anything else, you can use the chat function to connect to me, and I'll kind of filter questions through to Jim as they come. You should have all had a poll pop up when you first popped in that gave you the option to subscribe to our e-news or to just be emailed a link to the recording of this webinar if you'd like. So if you didn't get a chance to fill that out, please do so we can stay connected with you. And speaking of staying connected, I should note two things. One, this work that North House is doing has been made possible by the incredible community of donors and supporters who are behind the school as we figure out this new reality. If you'd like to make a donation or be part of that community, we welcome your support. I'll post a link in the chat function that would take you right to the donate page. This is a really hard time to be a folk school, and we feel really fortunate that we're figuring it out day by day. And the other connection piece is that if the internet breaks, which given how the world is going, maybe that will happen at this moment, Jim and I will reconnect later and record this session and then email you a link to it. So if Zoom for some reason breaks down, don't worry, it's unfortunate, you'll have to do something else over the lunch hour, but we will make sure that you get a chance to see this webinar. So that should be everything I wanted to tell you. So without further ado, I will introduce Jim Miller. Jim has been teaching at North House for, I think Jim will have to speak to this, at least 5 or 6 years now. He is a professor emeritus from the University of Minnesota Duluth and a senior geologist with the Minnesota Geological Survey. He has conducted geological research and led field trips for the last 35 plus years and retired in 2016 from UMD, but has joined us at North House following that. So without further ado, the geological story of Lake Superior.
Okay. Well, thanks, Jessa, and welcome everyone. I'm happy everyone could virtually join in today. I actually checked the weather this weekend when the What's This Rock class that this was kind of based off of was supposed to happen, and it would have been a really great weekend, but that's the way it goes. One thing I've learned is that the rocks aren't going anywhere. They'll be there for us to look at some other time. So we just have to be patient. So what I want to present today is the geological story of Lake Superior. And it's really can be paraphrased in basically a tale of fire and ice. And I will kind of break that into sort of two parts of the talk. Initially, I'll talk a little bit about some background information. And if I can, oh, sorry. So this this field of geology, people are very curious about it, which kind of why I put this, the title of the class I teach is What's This Rock? It's not a very intuitive science. Unlike biology, where you kind of know the changes of the seasons and life cycles and so on are very obvious to us. Not so much in geology, and there's a lot of jargon and terminology. And really, it seems like, except for the occasional catastrophic thing like an earthquake or a volcano or a catastrophic flood, the Earth is kind of just inert. It's not really doing a whole lot. But when you learn the language of rocks and you learn about geological processes, and then you learn how to recognize time in the rocks, and actually you can date rocks now fairly precisely, you all of a sudden see this great story over 4.5 billion years that tells these incredible tales of all kinds of phenomenon that happened on the Earth, and you realize the Earth is a really dynamic place, geologically speaking. And so, indeed, it's really kind of helpful to think of the book, I'm sorry, of the Earth as sort of a great ancient text, and it's divided up into different chapters that have been preserved, and a lot of them are missing, so you have to kind of piece the pieces together. It's very much detective work. You go out there and try to read the rocks, unravel the story the rocks are trying to tell you, and build that into the geological story of the Earth. So what we're going to do, and it tells incredible tales, and we're just going to focus on two of those tales today. Here's a geological rock column time scale for Minnesota with the geological map of Minnesota. It's very simplified, but it shows that the Earth, we have a pretty good idea, is about 4.5 billion years old. And there are different rocks that age out at different times throughout the rock column. The oldest rocks are in the southwestern part of the state in the Minnesota River Valley, and they have ages that are over 3 billion years. So some of the oldest rocks in North America. And then the area in northern Minnesota, the green and the pink here and some of the blue, these are part of a terrain that ages out at about 2.7 billion years. And this is a time when North America kind of got put together. The main part of the North American continent was organized about that time. And then about 2 billion years ago, we were on the edge of that continent, and we were depositing sedimentary rocks, including iron formation. The Great Mesabi Iron Range was deposited. This black Shazam line here was deposited then. And then you can see here in northeastern Minnesota, the brown rocks, those are part of a system we call the Midcontinent Rift. And that's what we're going to focus on today, is that story of lavas erupting from the Earth a billion years ago. And then we've got younger rocks to the south. Just these tan colored areas are covered by very flat line sedimentary rocks of different ages running through what we call the Phanerozoic eon. And the limestones and the sandstones you see down in the Twin Cities, those are these strata of Cambrian, Ordovician, Devonian sedimentary rocks. But we don't have any of that up here in northeastern Minnesota. It doesn't really play a factor in the story of Lake Superior. In fact, the second chapter we're going to focus on is up here at the top of the time scale, just the last less than 2 million years of Earth history when the Ice Age came into play. And that really is the ice part of the story. So moving on, I just want to go through some concepts, just so some understanding of some basic terminology and geological processes that help us understand the story. So this is a diagram that illustrates the dynamism of the Earth and the fact that we've recognized for the past 300 years of looking at rocks on the Earth's surface that the Earth is constantly recycling itself. This is just showing us how the different three main rock types, igneous rocks over here on the left, and sedimentary rocks on the Earth's surface, and then metamorphic rocks that are subjected to heat and pressure. They are all kind of interrelated to each other depending on the route they travel on the Earth's crust and in the Earth's crust. And so I'm not going to go through the details here, but this is something that is a very useful construct to understanding the relationships of the main rocks that we see that form in the Earth. We're going to focus mainly at dealing with the igneous realm here, from magmas that are generated from melting of the Earth's mantle, and then it's cooling and crystallizing either deep in the Earth. We make what we call intrusive rocks, or erupt at the surface and making volcanic rocks. And in fact, again, jargon is a big complication in conveying all of this to people not familiar with the language of rocks. But when you break igneous rocks down, there's really just 4 rock names that you need to kind of know what they are. And it's based on 2 criteria. One is the composition. It's a very magma is basically molten rock. It's a very complicated composition, but it's not a random composition. There are 2 kind of end members. One is a high temperature end member that we get when we partially melt the Earth's mantle, and that's called mafic magma. I always tell my students, melting the mantle makes mafic magma, always. At the other end of the spectrum is a rather high silica magma, lower temperature, has a lot of dissolved gas in it. Those are called felsic magmas, and they tend to be formed by remelting crust. And so we have these 2 end member compositions, and then we can place them into different parts of the crust. If we erupt them onto the Earth's surface, they cool very quickly, and that causes them to have fine-grained minerals in them and some gas bubbles. And so these would give rise to these 2 rock names. At the mafic end, we call them basalts, and at the felsic end, we call them rhyolites. Now, if we took that magma and instead of erupting at the surface, we intruded it somewhere into the crust at some depth, it loses heat very slowly, and this promotes the development of coarse-grained crystals that you can make out with the naked eye. And so basically the same mafic magma that came from the mantle, although it would make a basalt at the surface, a fine-grained basalt, it will make a coarse-grained rock we call a gabbro at depth. Same with felsic magmas. At depth, it will make a coarse-grained rock we call a rhyolite. And what we see are these minerals that will crystallize this assemblage of minerals, and that gives us a clue as to what kind of magma it came from. So really, with these 2 criteria, the environment of where the magma was put and the composition of that magma, you can classify all the igneous rocks on Earth in a very simple way. Another concept to understand is the plate tectonic theory. I really date myself all the time now when I tell people that when I took geology back in the 70s, in the early 70s or mid 70s, I guess, we were learning out of an introductory geology textbook, and it was the first time they put a chapter on plate tectonics in that introductory textbook. And it was sort of like, this is a new theory and it remains to be tested. Well, plate tectonic theory has the status of what we call a paradigm. It's not questioned. It's just embellished with details of various studies. But it is to geology what genetics is to biology. It's the great unifying theory that explains all manner of phenomenon on the Earth's surface. And it basically, the basic tenet is that the Earth's outer shell, which we call the lithosphere, or the rock sphere, is composed of rigid plates that are moving relative to each other. In some places, like along the center of the Atlantic Ocean, the plates are separating from each other. They're moving away from what's called the Mid-Atlantic Ridge. Well, if plates are moving away from each other on some part of the globe, and the globe is fixed, a fixed sphere, they must be coming together someplace else. And that's happening, for example, along the western margin of the Americas, and along the western margin of the Pacific, and so on. Just looking at that in a little more detail, taking a slice through the southern part of the Atlantic Ocean. Here's the Mid-Atlantic Ridge, and new magmas are coming from the Earth's mantle and crystallizing along that ridge and making ocean crust. And then that's on like a conveyor belt that's spreading. Africa is going east, South America is going west. And on the western edge of South America, it's running into a plate coming out of the Pacific that is subducting underneath the edge of South America, which is giving rise to volcanic activity and earthquakes and mountain building. So in fact, so these are called convergent boundaries, where plates are joining together. And as I say, this gives rise to all kinds of interesting geological dramatic phenomenon, like explosive volcanoes and earthquakes of various size and depth, and of course, mountain building by the scrunching up of the edges of the crust. And there's several kind of scenarios where you have this convergence. You can have an ocean crust plate, which is rather thin, colliding with a thick continental crust. This is akin to what's happening, again, along the western margin of South America. So this is South America. This is the Pacific Ocean. And as it goes underneath, it gets heated up in the Earth's mantle, partially melts, and then invades into the overlying crust and generates volcanic activity. And every time that plate slips along that subduction zone, it triggers an earthquake. You can have a situation like this also, where you have ocean crust going underneath other ocean crust that may be the leading edge of a continent. This is something like Japan. This is like the Japan arc here, and this is China behind it. A third type is what's called a continent-continent collision. Now, while ocean crust can easily fall back into the mantle and partially melt, it will, when the continental crust is made up of much lower density material, and so when continent runs into continent, they basically suture themselves together. They can no longer, the continental plate cannot go in the mantle, so they just build an incredible mountain belt, over thicken the crust significantly, and this is what's happening with the Himalayas, as India is sliding northward and colliding with the southern margin of Asia. Now, the other kinds of boundaries, divergent boundaries, where the plates are separating, this very commonly starts on continents. It's called, the separation is called rifting. And so we'll get kind of a spreading of a continent, and as it separates, magmas partially melted from the mantle, which make mafic magmas, remember, will fill that void, that breach in the crust. And as it continues on, it will eventually evolve to creating an ocean basin between them. And you can see the progression to where we are, like this is, again, the Atlantic Ocean down here. This is something akin to like the Red Sea as the Arabian Peninsula slides away from Africa. And there's basically basalts and mafic rocks, gabbros, and so on down at the bottom of the Red Sea. So this is a process that's going to play heavily into our story here in the Midcontinent. So one of the recent examples of this continental rifting and breakup of continental material began in about 250 million years ago. There was this what we call supercontinent, where all the continental masses had accumulated and accreted to each other, and they formed a huge continental mass called Pangaea. Starting about 250 million years ago, this separated. And so by 200 million years, you start to see the open Asia and the southern landmass, Gondwanaland. And all these gradually kind of separated from each other. It says my internet connection is unstable, but hopefully everyone's still with me. And you can see here's India, right? It used to be tucked between Antarctica and Africa. It drifted away, and then it eventually collided into the southern margin of Asia. So this is an example of continental direct continental separation or rifting, creating new ocean basin. Finally, another important concept that is very helpful, we're dealing with rocks that are 1 billion years old, over 1 billion years old. How do we know what that would have looked like 1 billion years ago? Well, we basically use this principle we call uniformitarianism, which can be summarized as the present is the key to the past. If we want to understand processes related to the separation of plates in rift zones, we should go study the East African rift that's happening today. Or we should go into the middle of the Atlantic Ocean and study the volcanism of Iceland. Or we can go out to Hawaii and look at the way that magmas are coming through the crust to build the islands of Hawaii. And we'll see incredibly similar features on these lava flows that we see in these current locations. And the compositions, you can take a piece of North Shore basalt, analyze the chemistry of it, it would look exactly like a basalt coming out of Iceland or Hawaii today. So this is a very powerful concept that we use all the time when we're looking at old rocks. So let's go with the first part of the story. About 1.1 billion years ago, yep, that's a lot of zeros in that number there. This is how basically North America looked. It's a landmass we call Laurentia. It actually included Greenland. Were all merged to what is now North America. And you can see it's composed of other terrains that came together at different times. The core of it are these granite greenstone terrains, like in northern Minnesota, between 3 billion and 2.5 billion years old. And then it's mantled by rocks that including the Mesabi range that formed between 1.6 and 1.9 billion years, and added terrains, smaller, older terrains were merged in as well. There's a younger terrain still, about 1.3 to 1.6, largely buried in the center of the US. And at this time, there was a mountain belt being created. This isn't the Appalachians. This is a mountain range called the Grenville. We see these rocks exposed today in upstate New York and the Adirondacks and all through eastern Quebec. It's largely buried to the south. The Appalachians don't come into play until about 400 million years ago. This is 1.1. And there were no Rocky Mountains. The Rocky Mountains simply did not exist at 1.1 billion years ago. So we have this continent, and what appears to have happened is we've seen this through many periods in geological time where there is a hot rising plume that has this sort of shape down here, this mushroom-shaped head rising from the core mantle boundary some 2,000 kilometers below the Earth's surface. And when it impacts underneath the Earth's crust, it outlets an incredible amount of magmas, most of them that erupt to the surface as basalts. And this is what we think happened in this area about 1.1 billion years ago, underneath what targeted right on top of what becomes Lake Superior. Now, what we call Lake Superior is a very recent thing. It's only 2 million years old or less. So this is 1 billion years ago. A lot more zeros related to that. And here off to the east. Yes.
This is Jess. I apologize. There's a little bit of a delay in your video. Do you want to stop your video? Because what we really need right now is your audio, and I think it might solve that problem. Apologies to folks. I don't know if other people are experiencing that. So we'll just do your face, but we'll hear your voice.
Take my face off? Okay.
I think it'll reduce the amount of data your computer's trying to move.
Okay. So
okay, thank you.
So I mute the
video.
Stop video. See, everyone can still see the.
We sure can.
Okay.
Lake Superior, only 2 million years ago.
Right. Yes. So again, there were this mountain building event going on to the east, making the Grenville. We'll talk about that later. So what happens as this very hot pipe of mantle comes up and impacts underneath the crust? It causes the crust to separate in these two main arms and rupture, and into these ruptures spill layer upon layer upon layer of mafic magma making basalt flows. So kind of summarizing this in a progression, a cartoon progression, we have our mantle plume impacting underneath the crust and melting and rising through the fractures of the crust as it separates and erupting at the surface as basalt flows. Some of them pond within the pile of lavas and cool slowly to make a gabbro. And we're also making rhyolite. Talk about that later. But basically, million-year period. We've got really precise age dates up to like a 500,000 or less of accuracy in the age dates. After that 30 million year activity, we had this very thick wedge of dense rocks sitting in the crust that continued to kind of weigh the crust down and sag it. And into that sag, that trough, we piled a whole bunch of sand. And then we compacted that into sandstone. And if this had been a normal rift like the North Atlantic today, basically the right side of this block would continue to move off to the right, and we would be, we'd have an ocean basin between us. But instead, what apparently happened was a compressional event squeezed the rift back and actually brought a big chunk of it from depth towards the surface. So this is the we call this an aborted rift. So here's the geology in the Lake Superior region of the rocks created in the rift. The green are the lava flows up along the North Shore here and along the backbone of the Keweenaw Peninsula and down into the Wisconsin-Minnesota border area. And then the gabbros, the magmas that never made it to surface but ponded in big intrusions within the lava flows, form the brown here. And this large mass of brown here, this is called the Duluth complex. It's the second largest gabbro complex on Earth. There looks to be a lot of that as well up here in the Lake Nipigon region as well, but these are held up. If you've ever been up, I live right here. And I look outside my window and I can see the sleeping giant off in the distance. And what it is it's an intrusion that's very flat lying. It's only about 500 meters or less in thickness, but it holds up tabletop mountains. And that's what all this is. So it kind of gives you a false sense of how much material is here by the fact that it's at the surface, right at the surface, holding up resistant tabletop mountains. So these sediments that filled the rift are shown in the yellow. And then the compression basically brought some of these lava flows up in contact with those sediments that had one time buried them here's the Keweenaw Fall right here. So that's the general picture. If we look at northeastern Minnesota, again, here's our 4 main rock types broken up very simply, and our two ways of classifying them. Much of northeastern Minnesota is underlain by intrusive mafic rocks we call gabbro. The basalts are basically shown in the green here. These lava flows are gently tilted to the southeast. It's kind of like a saucer shape, arcing from northeast here down by Duluth, and then arcing through and then becoming more east-west and tilted to the south up by Grand Marais. There's a few rhyolite flows in the sequence, especially around Grand Marais. And then there are also some granite intrusions, coarse grained granites shown in the oranges. So the way these all kind of work with each other and the way we explain them is that we think that when the mantle plume was melting, this hot mantle came and partially melted, making mafic magma. A lot of it actually ponded at the bottom of the crust and made a big magma chamber there. And this heat, this 1200 degrees centigrade of magma, was it hot enough to actually melt the bottom of the crust? And again, when you melt the mantle, you make mafic magma. When you melt pre-existing crust, you make felsic magma. So we took that felsic magma and we could intrude it and make a granite intrusion at depth, or we could erupt it at the surface and make a very thick rhyolite flow. The mafic magmas would erupt. They could intrude also into the bottom, making gabbro intrusions, or they could have also erupted to surface to make a basalt eruption. Now, looking at kind of the way basalts erupt, again, when most people think of volcanoes, they think of a cone-shaped volcano and exploding eruptions and so on. But these, in Hawaii or in Iceland, they don't explosively erupt out of the ground. They fountain out of the ground. They fuse out of the ground. And a lot of times they're actually controlled by big fractures or fissures rather than a central cone vent. But they do have some amount of gas dissolved in them, and when they reach the Earth's atmosphere, that release of pressure causes the gas to unmix from the lava. And so as the lava flows away from its source, and it's very fluid, it spills out like pancake batter over the surface. You've seen pictures of Hawaiian eruptions. That gas is basically bubbling through the lava flow. The interior of the flow stays hot enough that the bubbles can rise, but then the top of the flow is cooling against the air, and so those bubbles become trapped and they get frozen in. There's a few bubbles lava flow. So that's how we recognize one flow from the next as we go along the North Shore. Here is a basalt flow, the top of one basalt flow. Now, in this case, the bubbles, they basically are holes. Well, nature abhors a void space, especially as it gets buried. So what happens, these holes get filled with lower temperature minerals. And they create what we call amygdules. And there's a variety of minerals that make amygdules. And we call the rock an amygdaloidal basalt. Sorry for the jargon. Here's the basalt that sits on top of it. A bit of in the bottom of that flow, gas bubbles get frozen initially, but then you can see as you move up a little bit, here's a pencil for scale, that the basalt is basically devoid of bubbles. And so this is a very amygdaloidal top, sharp contact, and then basically massive non-amygdaloidal basalt sitting above it. The types of minerals that fill amygdules are plentiful. They crystallize usually from hot waters, not magmatic. They're not magmatic. They don't come from magma. They come from actually hydrothermal solutions. And they've got lots of minerals dissolved in them. And then when they cool, they'll precipitate those minerals in those gas bubbles. So a very common one is a mineral called zeolite, of which there are a whole variety of particular zeolites. One variety, the most sought after, is the mineral thompsonite. But there's others, this greenish mineral called epidote, and this pinkish mineral of feldspar, this blackish greenish mineral called chlorite, or other kinds of amygdal fillings. But by far the most interesting amygdal filling is basically quartz, a mineral that is called cryptocrystalline quartz, or we know it as agate. And when we see agate in basalts, they're typically, if it's a nice fresh basalt, you'll see the agate is white. If you get up close with a magnifying glass, you can see the bands, and sometimes they'll be painted slightly, but you can see the rock is also kind of turning red. And here is an example of how we usually find agates. They've been liberated from their host basalt and brought out by the glaciers, and they are nicely polished, and they're shiny and glassy, and they have that classic red color. So what we think happens with agates is that there are these small gas holes in the basalt, and then in this case, solutions very rich in silica move through there, and they start to paint the inside of the gas bubble with a thin silica gel, layer after layer after layer. It fills it up. Sometimes at the end, the crystals will form coarse grain crystals like a geode, and they'll grow inwards. They could sit there for millions and millions of years, but when that basalt is exposed to the surface and starts to encounter oxygen and gets weathered, the basalt has about 8 to 10% iron in it, and that iron gets oxidized, rusts basically, and that rusted iron paints the agate its classic red-brown color. Another thing that you would find on basalt flows commonly that you would see today in Hawaii or in Iceland is a surface from these very fluid lavas. They develop this rippled surface that in Hawaii they call pahoehoe. And here's an example of pahoehoe on the North Shore. You can see the nice ripples. You can tell the lava was kind of being pushed and curled up from underneath, from the lava flowing underneath that surface. There's also flows in Hawaii that look more broken up. The basalt is much more fragmented, and that's called an a'a flow. And here's a'a on the North Shore. All the interstitial spaces here now are filled by dust, by windblown silt. So all this light tan color, and the greenish with the speckles in it, those are fragments of basalt. So we have both varieties of basalt flow types in billion-year-old rocks, similar to what's happening today in Hawaii and Iceland. We also have the other kind of volcanic rock, the felsic variety of volcanic rock we call rhyolite. The most famous flow on the North Shore is called the Palisade Head rhyolite. It makes up Palisade Head, which is over 200 feet thick, one individual flow. It also holds up Shovel Point, and it also holds up the highest waterfall in Minnesota on the Baptism River. And rhyolites are very thick. A normal basalt flow is maybe on average about 5 to 8 meters thick, whereas rhyolite flows can be 100 meters thick. It's because rhyolite magma, felsic magmas but they don't flow easily, so they tend to pile up into much thicker sheets than basalts do. The intrusive rocks of the rift are found all throughout northeastern Minnesota. This is kind of breaking up that one image you saw, the yellow, and that other image showing where the gabbros are. We can tease out individual intrusions of gabbro all throughout northeastern Minnesota. The big mass here outlined in the dashed line is the Duluth complex, made up of dozens of individual intrusions all amalgamated together. And then higher up in the pile, we have other intrusions that we call the Beaver Bay complex, shown here in the orange. And these are just intruded higher up in the volcanic pile. And coarse grain gabbro and coarse grain granite. We also have sedimentary rocks. We don't see good examples of sedimentary rocks like you see on the South Shore along the Keweenaw Peninsula or the Bayfield Peninsula. If you've ever been out in the Apostle Islands, you've seen all those red sandstones out there. Those are these sandstones that had buried the lavas at one point. On the North Shore, the only time we see sediments are in places where there's been a hiatus in volcanic activity, and then rivers would flow into the trough and lay out layers of sand that then would be buried under another lava flow. We call them interflow sediments. And here's the most classic example, just south of Grand Marais, by the Cutface Creek. Nice thick sequence of interflow sandstone, siltstone, and then over the top of it, protected by a very thick basalt flow called the Terrace Point basalt. And we stop there all the time for our What's This Rock class. So finally, again, if this had been a normal rift, we would have expected that the east side of the rift would have gone and been its own continent, and we would have been left with a ocean at our front doorstep rather than a big lake. One thing, but we had this compressional event that basically reversed that process. And what it did, here's in this little exposure right here on this cross section, you can see the basalts that were at one time buried underneath the sediment, all of a sudden by the compression gets shoved up along this fault and is juxtaposed against the sand which had one time buried it. And we can see this in a very rare example at Amnicon Falls State Park, just outside of Superior, Wisconsin. So the falls themselves right here are held up by basalt. And then downstream of that, these are relatively weak rocks of sandstone. And whenever you see a waterfall, it's usually you've got a resistant rock next to a non-resistant rock. And that's certainly the case here. But you can actually, the stairs take you right down, and you can put your hand on the basalt, and you can, on the, below you can put your hand on the sand. In that space, one side of the earth, to the sandstone underneath it. So it's just incredible that you can see that exposure. Most faults are not well preserved because it's broken up rock, and the glaciers came through and scoured that out, and so you very rarely see it. So this is a very unique exposure to visit for sure. So it begs the question, you know, it happened that the continental separation didn't go to completion, and if it had, Duluth would be a seaside resort. Why didn't that happen? Or, as I always like to point out, why is Wisconsin still with us? By all rights, it should be its own continent, and we should be a luxury seaside resort. But no. And it's because of this Grenville orogeny, this Grenville event that happened to the east of us. So there was a block of what's now part of South America called Amazonia, was running into a piece of itself before the full collision happened with Amazonia to evolve the rift. But then eventually the collision of Amazonia against this inner Laurentia block shoved everything back on itself and aborted the rifting. You know, even though we still have Wisconsin, this is a good thing, because now in the Midcontinent, we have preserved in the Lake Superior region rocks that tell us the story of how continents break apart. It's an incredible natural laboratory. Okay, let's cool things down a little bit. We're now going to go to the very end of the geological timescale, something that happened just less than 2 million years ago, not billions of years ago. A lot less zeros in that number. And that is during the Ice Age. It was commonly thought that there were 4 major, out of Canada and into the northern part of the US. However, we now know that actually there are probably more than 25 individual glaciation cycles that happened over the past 2 million years. And you can see this data record here from oxygen isotopes, which are very sensitive to temperature, are really good markers for when the Earth gets very cold. This is the extent of the ice sheet and the last major advance, called the Laurentide advance. And this is at its stage at about 14,000 years ago. And really, everything about Minnesota, the entire landscape, our entire physiography, is related to the effects of glaciers. So they're very important. Like to think of nature. Ice is incredibly strong, and the upper surface has a slope to it. As it moves to the south, it will cause the ice internally to flow to the ends of the glacial ice. In mountains, it flows down a valley, so it's got that natural push. But in continental glaciers, when they're so thick in the central part of Canada, sometimes the ice sheets were over 2 miles thick, maybe even 3 miles thick. And then they wedge out to thin edges as they cross down across the border. While they move very slowly, they pick up fragments of the material that they're flowing over, and they draw them into the ice. And when they hit the margin of the ice will melt, and it will dump its sediment load at the edge of the ice. And there's sort of what will happen depending on the balance of how much snow is accumulating over seasons versus how much melting happens over those seasons. If there's more, it will grow southward. If there's more melting than there is snow accumulating, it will retreat. The edge will move back. However, during retreat, the inside of the ice continues to flow down to the edge of the ice. So it's almost like it's laying out a carpet of sediment as it retreats. If it advances, it basically runs over everything it just deposited, reincorporates it, and then starts all over again, laying out this sediment. And all kinds of glacial landforms are evident in the retreating depositional phase of the glacier. And won't go into those, but those are features you've heard, like moraines and eskers and kettle lakes and so on. This ice that has incredible amounts of sediment drawn into it is basically like sandpaper. The bottom of the ice is laden with 50% of fragments of boulders and silt and clay and sand and cobbles and pebbles, all piled into the ice, all packed into the ice. And as it moves slowly across rock surfaces, it has the ability to polish them off, plane them off. And in fact, here's an example of what's called glacial polish. It polishes that surface by just the slow grinding of this very abrasive base of the ice sheet, and it scores the rotations, which is great because it tells us the direction that the ice was flowing. Here's a great example on the North Shore. Here's some basalt. It's got these striations, and then overlying it is classic material deposited from glacial ice, material we call till. The most recent advance of ice basically happened in there were several tons of ice, called ice lobes, that came from different parts north of the border. What we see here on the North Shore basically came through sort of the northern end of the lake. It found the Midcontinent rift, this trough of sand basically, and started to work its way down and start to scour out the Lake Superior Basin. And it picked up basalts, it picked up agates, and all the things that are mantling the Lake Superior geology, and distributed them. Some of the best agate hunting is actually down in the Twin Cities. And even as far south as Iowa. So the ice that came out of Lake Superior must have traveled at some point down at least that far. Other ice came out of right in the Boundary Waters area. It's picked up all kinds of old 2.7, 3 billion year old rocks and deposited them through this area here in the dark green. And then another sheet of ice came out of Manitoba and eastern North Dakota. And it was picking up pieces of limestone and shale. And it distributed them all across western and southern Minnesota and to the north central part of the state. You can see the deposits of that shown here in the green. Just so happens that's some of the best agricultural land in the world. So these glaciers basically custom mixed like the perfect soil for making really good agricultural land. The stuff that came from Ontario, the rainy material and the Lake Superior material, made sediment that's very sandy, didn't have a lot of clay in it, didn't have any lime. So it was more promoting the growth of coniferous forests. And that's why we see such a difference and such a relationship between the glacial material and the type of the biome that was developed on those soils. We are the land of 10,000 lakes, although it's a whole lot more than that. And there's ponds and swamps and marshes and all kinds of wet places on the landscape in Minnesota. There's kind of two main ways that we made lakes in the state. In areas where there's a very thick accumulation of glacial material, glacial till. Very commonly, blocks of ice would get stranded in the glacial material, water, and those are called kettle lakes. Up in the Arrowhead area, in the Boundary Waters, what makes it so spectacular is that here the till cover is very thin. And so what happens is the ice was in a very erosional mode. And so the reason we have these linear lakes is that these are old fault systems in ancient rocks that the ice has accentuated. And so it makes a much more geometric pattern that's controlled by the structure in the rock. Not so much in like central Minnesota where it's just these irregular kind of lobate shaped ponds and so on. However, these are little ponds. The big lake that's right outside our door. The whole glacial story that I think. What happens starting about 12,000 years ago was the ice sheet, the Laurentide ice sheet was in retreat. It was moving back, but it ran into a point where the edge of the ice stayed fixed for a time. And so it conveyed all this dirt and built up a moraine. It's called the Nickerson Moraine in eastern Minnesota. And eventually the lake then the ice started to retreat to the northeast. And so it got dammed up behind this earthen dam of this moraine. And it caused the lake to fill up to a level we call Glacial Lake Duluth level. If you're in Duluth, Skyline Parkway is basically the beach of Glacial Lake Duluth. By about 9,500 million years ago, the ice, the eastern outlet of the lake was blocked. But by 9,500 years ago, that opened up and the water basically surged out and dropped to a level we call Glacial Lake Houghton level, which was much lower than the level today. Over the past 9,000 years, the lake level has finally come to its present level of 600 feet above sea level. looking at this graphically, so starting about, again, 12,000 years ago, the lake was full of ice. It started to retreat. And as it did, again, the eastern outlet, it's Sault Ste. Marie, was blocked. And so it filled up to a level about, here's the present lake level, 600 feet above sea level. So about 1,100 feet above sea level was Glacial Lake Duluth. And as the eastern outlet started to open, and a couple things were happening. As the ice was removed, the crust started to lift. It was called glacial rebound. The weight of the ice was gone, and the crust started to relax and lift up. And so when the ice finally left to the east, the whole basin was tilted that direction. And so it basically emptied to a point that is about 350 feet above sea level. We call Glacial Lake Houghton level. It did this in the span of just over 1,000 years. You can get your head around 1,000 years. In fact, there are many tales in Native American lore about the moving lake waters and how they would kind of move down the hill. Over time, then the eastern part of the lake started to rebound when the ice had finally left, and it tilted everything back to the west and brought it to its present lake level at about, again, 600 feet above sea level. So pretty incredible story. So just to encapsulate the whole picture here, Lake Superior is there. You can see it mimics the trend of this arcing Midcontinent rift system of rocks. And the fact that it had, in the core of it, had a lot of this sand, right? And so when the glaciers came south and encountered this big wedge of relatively erodible sand, it decided to move to the southwest and scour out that basin. The bottom of Lake Superior is many, many hundreds of feet below sea level. And when you see a hole in the Earth's crust that's lower than sea level, the only thing that could have done that was ice. And some odd tectonics perhaps, but this is great evidence that this was scoured out by glacial activity over the past 2 million years. So just putting this again back in our cartoon, got our mantle plume generating lava flows, intrusions of gabbro over 30. We cap that off with a thick wedge of 10 kilometers of sandstone. And rather than becoming a nice ocean basin, it actually collapses on itself and thrusts up this big central block, and things get frozen. It sits at the Earth's surface now for almost 900 million years. Nothing really, if anything happened, it's gone. All we know is that it just sat there and eroded and weathered and basically waiting for the ice to show up. And that happened about 2 million years ago, big thick sheets of ice. It had an easier time grinding out the sand compared to the nice crystalline basalts that were on the flanks of the rift and holding up Isle Royal and the Keweenaw Peninsula. And so this gives rise to our present cross section across Lake Superior today. So that's our story. And I'm happy to take any questions at this point. So thank you.
All right, Jim, it looks like we've had a few questions come in that I will go ahead and send your way. Let's see. Sarah Nassif is curious about cames. The hill in Minneapolis with the Witch's Hat Tower is a came, I think. I would love to know how common they are.
Okay, that's a great question. Yeah, cames are one of those landforms that form in areas of kind of dying ice at the edges of the ice sheets. A lot of times the water that's flowing on top of the ice as it's melting will kind of tunnel itself down through the ice, and it will carry sediment with it. And then it fills that hole with sediment, and it builds up into the ice as kind of a column of sediment. And when the ice then melts away, you're left with this mound that was the vertical tunnel that was formed from that. That's I think the typical way that you make a cane.
Great. And I think if you don't mind, you can stop sharing your screen, and then if we should be able to see you again, and hopefully the video will keep up with us.
Okay.
So there, everybody. So if you want to, let's see if we can make this happen.
Stop share. Oh, okay.
You are. All right. Let's see. Pamela asks, were the other Great Lakes formed similarly?
Great question. Yes, they were basically excavated by the glaciers. And notice that most of the Great Lakes have lobate shapes, like the southern end of Lake Michigan. That was that tongue of ice that was coming through. And it just so happens that there's resistant rocks on the Wisconsin side. Limestone is a fairly resistant rock compared to the rocks that it's embedded with. And so the limestone holds up the eastern shore of Lake Michigan, and also is again on the western shore and on the eastern shore. And in between was very weak rock, some shale, which the glaciers found very easy to erode away, and that made that trough. But look at all the lakes, and you'll see that they all have these kind, like Saginaw Bay, is another little lobate arcuate remnant of the scouring out of Lake Huron.
All right, great. Let's see. Mary asks, is the bottom of Lake Superior igneous, and what type?
If you, at the bottom of Lake Superior, it actually, some of the most incredible data that we got that helped us understand the Midcontinent rift was accumulated in the late 80s. It was a joint project between the Canadian Geological Survey, the US Geological Survey, Minnesota, Wisconsin, Michigan, and Ontario, where they ran seismic reflections across the lake. And seismic reflections allow you to see layers in the crust. And so these lava flows, we know, like on the North Shore, they tilt to the southeast, and when they get under the lake, when they come to the Michigan side, they curl back up the other way. And you could actually, in those reflections, you could see the layers of lava, doing that, and you can tell how thick they are. And you could also see the sediment that's on top of it that's still preserved down there. So I think most of the bottom of the lake has still got some sediment, some sandstone still there that sits on top of the lava flows. It wasn't completely excavated out. So I would say most of the lake bottom is sandstone. But if you drill through that, you'd come back into lava flows.
Great, the questions keep coming in. Let's see, Gary asks, south of Superior is Camp Pattison, where there is a waterfall, and the explanation there is that there's a fault line going into the Twin Cities. How does this fit with your explanation?
Okay, well, that is the same fault that you see at Amnicon, okay? So it's where you have brought up these basalts from depth up into the sandstones, and now they're juxtaposed to each other. Sandstone, like the glaciers, had a really easy time grinding out the sand and to make the basin. Basalt is a very resistant crystalline rock. And so, and again, waterfalls are, whenever you see a waterfall in nature, it's because there's a hard rock next to a soft rock. And the river's having an easy time cutting one and not the other. And so it makes a nick point in the profile of the stream. And so that fault, it's called the Douglas Fault. You can trace that all the way to the south to through past Hinckley and all the way to the northern end of the Twin Cities.
Great. Oh, Kathy Smeets has a great question. What conditions bring about volcanic eruptions flowing slowly, resulting in rhyolite?
Well, it's really a function of the composition of the magma. Again, because of the high mafic magma that you generate by melting the mantle, it has about 50% silica and lots of iron and magnesium and calcium and aluminum and a whole soup of elements. Rhyolite has like 70 to 75% silica, and silica is, we call it, it's a polymerizer. It likes to stick together. The silicon oxide molecules don't like to be separated, so it makes a very viscous magma. So when it erupts, it doesn't easily flow downhill. It winds up freezing before it travels too far. So, and another way rhyolites erupt, sometimes they come out like that as magmas, very sticky magmas, but sometimes they're because there's so much gas in them, they don't fountain out of the ground like a basalt does. It explodes out of the ground and it pulverizes the magma into ash, and then the ash settles down to the ground, accumulates one layer on another, and then it kind of gets heated up by the accumulation of this hot ash, and then that ash starts to flow down the slope, and that's a different kind of a rhyolite kind of eruption.
All right, another question about rhyolite. Erica wonders about the very nubby texture of the surface of the rhyolite on Shovel Point, which seems to break off into small gravels. Are you familiar with that?
Yeah, I've been on Shovel Point. I think it's the top of the slope there on Shovel Point. You're not quite at the top of the flow. It has a kind of a rubbly, broken up flow top like most flows have, but that's been eroded away by the lake. And so all you have the massive interior that's pretty, other than vertical fractures through it, there's really not a whole lot of structure to it. I think it's the nubbly nature of it is just sort of the way it weathers, and maybe there's actually nubbly texture is something that's actually more common in basalts. There's a kind of basalt that is called ophitic basalts. Sorry to throw terms out, but it's basically, it's got knots in it that are mostly held together by this one mineral, pyroxene. And so when it weathers, you get these almost like ball bearings of these clusters of these pyroxene knots. Anyway, it's a very common thing, and that's really, again, honestly, when you're out there doing field work on an ophitic basalt flow, you better watch your step, because your feet will just go out from under you and you'll just wind up on your butt.
All right. Let's see here. Bob King. Hi, Bob.
Hey, Bob. How are you?
Except he looks up and not down.
Yes. Yeah.
Yeah. Astronomy instructor.
Bob looks everywhere.
Yes.
Bob's a great naturalist.
Wonderful. Well, Bob asked a clarification question. Was it the rise of the Grenville Mountains to the east that stopped the rifting?
Yes, that's thought to have basically arrested everything. And again, the Grenville was caused by what we now know as part of South America, a crustal entity we call Amazonia. It broke away when the Atlantic, or before the Atlantic opened up. And then it moved south of North America to its present position. But there was, I had this one slide that I knew I had to take out because I could spend way too much time talking about it. But about 1 billion years ago, there was a construction of a new supercontinent, new to us. It was an old supercontinent called Rodinia, and Laurentia was at the center of it. And there were all the continents of the globe basically docked in alongside of it. And one of the dockings was this cluster from Amazonia and the Rio Plata, and then to the north there was what's now Scandinavian countries. It was a continent called Baltica. They all kind of merged together. And again, I could go on about this part of the story. I showed the rift sort of forming from kind of the impact of a single mantle plume thing. Well, now we're actually thinking, and that still may be the case, but what we're more probably familiar with now is that because of the construction of Rodinia, the effect of that is to insulate the mantle, right? So you've got continental crust that's 40 to 100 kilometers thick, depending on if there's mountains on it or not. But heat has a hard time conducting through continental crust. It easily conducts through ocean crust. So if you put all the continents on one side of the globe, it's like throwing an insulating blanket on one side of the earth, and you keep the heat in the mantle. It can't escape. So you develop these superheated bubbles of mantle. And we think that's how the continents break apart, is that we basically overturn the mantle. We have this great rise up of the mantle, we call them super swells, and they just basically they break that supercontinent apart and send it, traveling off in various directions. And eventually they recollect on the other side of the globe and we make a new supercontinent. And then that overheats the mantle, and then that breaks apart and goes around. So we think about every 500 million years we've had one of these supercontinent constructions, and then breaking up and reconvergence.
Great. Folks are putting you through your paces here, Jim. We've got a lot of questions.
I'm good with that.
All right. Can you tell us the story of how and why the St. Louis River used to flow into the Mississippi River when Lake Superior was filled by the glacier?
Yes. Well, and actually the St. Louis and the Brule, like in Wisconsin, they used to flow south into the Brule flowed into the St. Croix drainage, and I think the St. Louis may have as well. When Glacial Lake Duluth was at that high level, there was no outlet north or east, right? Or to the south. It was up to the brim of that moraine that was holding it back. So it found sort of low points in the moraine where it could drain to the south, and it did that for a time. And then when the lake level finally subsided, those rivers reversed course and they flowed to the north into the subsiding Lake Superior Basin.
All right. Let's see. William Runquist notes he says, thank you so much. And he had a bunch of questions, but you answered them except for this one. Generally, how and when did the limestone in Minnesota form? Doesn't limestone form in oceanic environments?
Absolutely. And that's what it tells us, is that there was an ocean of the limestones in southern Minnesota are several general ages. Some are, or if you look back at that time scale I showed, most of them are Ordovician, but some are Devonian, younger. And so these formed when the interior of North America was flooded with shallow seas, and North America existed at the equator. So you need water, you need ocean water to deposit limestone, but you also need high temperatures to cause evaporation that then causes the calcium carbonate to precipitate out of the seawater. And so North America sat at the equator in the Ordovician period, right through Minnesota. The equator passed right through Minnesota. And east was, what's present day north was actually pointing east at that time. And so all throughout that period, in the Paleozoic time and Ordovician period and the Devonian period and Silurian, even all these ages of that period, we were under shallow water. We call them epicontinental seas that flooded the interior of North America.
All right. Aunt Randy asks, in the Minnesotan context, are there any substantial interactions between the biosphere and geological processes? In other words, do living systems impact geological systems in this geographical location?
Oh, absolutely. If you go and look back at that rock cycle illustration, you'll notice that the surface material, that stuff at the surface of the crust, they're interacting with the hydrosphere and the biosphere and the atmosphere. And there's, all of that is going on to break the rocks down and turning rocks into soil. And then you can transport that soil and redeposit them somewhere else and make a new sediment and cement it together and make a sedimentary rock, and on you go through the rock cycle. So, but the biosphere is another agent for breaking rocks down. I mean, I apologize to anybody who really likes lichen, but I don't, because lichen just covers up the rock. I can't really tell what the rock is when I'm out in the field trying to identify the rocks, and you can't scrape lichen off. It's there. It's eating up the rock and gaining nutrients from the breaking down of the minerals of the rock. So, but the biosphere is definitely, it's helping to make soil and chemically break down the rocks.
In defense of lichen, I will note Lusky shared a fact earlier this week that lichen is the only thing that has been living thing that's been taken into space and exposed to outer space and then brought back to Earth and then came alive again. So
well, good on lichen.
When you start doing geology in space, apparently lichen will be a problem there too.
That's right. They didn't find any lichen on the moon. Got to say that.
There you go. Let's see. Bob also asks about the Caribou River bottom. Has a strange mix of soft rock embedded with cobbles. How did that formation form?
Okay, the Caribou. Okay, yeah, the Caribou is really an interesting geology through there. There's lava flows, but there's this weird lava flow it's a fragmented volcanic rock. It's called the Pork Bay Breccia. Breccia means broken rock. John Green, emeritus professor at UMD, my mentor, kind of coined that term. But it's really well exposed in the river bottom there at Caribou, not too far up from the highway. And it's a puzzle. We have lots of ideas of what it might be, but none of them are very gratifying. And then when you get up to the falls, Caribou Falls, we think that that face there is, again, all basalt. You can see you can actually see breaks in the cliff there, and those are lava flow contacts. And they're tilted very gently towards you, towards the lake. And we think that escarpment is there because of a fault, that there's a fault that runs along the face of that cliff there. You can trace it some distance to the northeast and the southwest. So, but yeah, the Caribou River geology is really quite remarkable. I would point out, if you're at all interested in the geology of the shore, most of the North Shore has had geological mapping done and geological maps made that are free to anybody to download a PDF of any quadrangle, 7.5-minute quadrangle on the shore. And it's, there's a lot of jargon and terms in there that are hard to decipher, but every now and again you'll see, oh, basalt, oh, gabbro, and you'll be able to kind of tease out what the basic geology is. And if you're curious, go ahead and download one when next time you go and hike up the Caribou.
All right, let's see. Any predictions of what the Lake Superior area will look like 2 million years from now, geologically speaking?
Okay, so another ice age worth, right? That is a really good question, because we are now in a period of time called the Anthropocene, which is the time of human influence on the geological record. I showed you that squiggly line that showed the glacial, interglacial oscillations over the past 2 million years. There's no sign in that record that was going to stop. And we're now in an interglacial period, but if we weren't around to put, heating agents into the atmosphere, that probably would just keep going. So we would be expecting another ice age to come around in another, 100,000 years or something, or 50,000 years, whatever it is. But now kind of all bets are off as to whether we are going to be breaking that cycle and in fact moving in uncharted territory.
Okay, which actually leads us to the question, where will the next continental breakup occur?
Well, I'm trying to well, right now, the only place where there's active continental breakup is in East Africa, and it's the East African Rift. It's not a very well organized rift. In fact, most of the major rifts that broke up Pangaea they're all established. The next major thing that's going to happen is North America and South America are going to continue to move to the west, and they're going to consume the Pacific Ocean. Asia and Australia are moving to the east. So in probably another 200 million years or so, those continental masses will merge, and they'll come together and close up the Pacific Ocean. There will be that's the thing about ocean crust. It's a very temporary type of crust on the Earth. It's always recycled. It goes into subduction zones and partially melts and adds material to the overlying crust. And so it's like the oldest, for example, we've got on the continents, we've got rocks almost like, I think the oldest material we've ever found is 4.2 billion, which is almost the age of the Earth, 4.5 billion. But the oldest material in the oceans is only 200 million years old, 200 million years old. And that's because the ocean crust, again, is a temporary thing. Plate tectonics is basically making crust by recycling, 2 stages of recycling. The mantle melts, makes ocean crust. The ocean crust go into a subduction zone. They partially melt and make continental material that adds to the crust. And so it's this sort of 2-stage distillation process of the Earth.
Okay, let's see. Are the ocean fossils found in Superior from Laurentia?
Ocean fossils found. Well, the oldest, the Cambrian is when we start to see fossil life, shells and such, exoskeletons and whatever, preserved in the rock record. And that's 540 million years old and younger. Prior to that, we had life on Earth, but it was very simple, single cell bacteria, algae, that kind of thing. We see structures like in the iron formations that we call stromatolites, which we know are built by mounds of algae. We see that material today, like in the off the Sharks Bay in Australia. There's stromatolites being built there by very primitive algae and very saline waters. At the head of the Persian Gulf, we've also got algal mounds that again, if you fossilize those algal mounds, they take the form of this material we call stromatolites. So we had very primitive life forms in this period we call the Precambrian, before the Cambrian explosion of life, but they were very simple, and they really had no preservable parts. There's material that we can attribute to their activity, but we don't see any shapes of them or whatever.
Let's see, William Runquist has another question. Are there any burning geological questions in Minnesota that have not been answered yet?
Well, burning means different things to different people. My area of expertise has always been the rift. So when I'm talking about glaciers, take it with a grain of salt, because I'm not a glacier person. I've studied igneous rocks most of my career. And I have, we're at a really interesting time. I mentioned that we had this idea that the rift formed from this single plume that impacted, into the crust and got everything going. But we now know it's more complicated than that. And the fact that the volcanic activity lasted 30 million years, there's lots of other places on Earth that we know were impacted by plumes that flooded out onto the surface. In fact, we call them flood basalts. But those only lasted like 5 million years at the most, not 30 million. So that's a bizarre thing that that the magmatism lasted 30 million years if it was just this one plume. So what we think is that actually the Earth's mantle was just really overheated, and we kept tearing away at Laurentia from pulling it and pushing it from different parts that basically caused it to break and let the magmas come through. There's a great scientist who's from the University of Minnesota, did his PhD there, is now at Berkeley, and he does paleomagnetism, which is basically, with that, you're able to figure out where the continent was situated on the globe, because it points to the North Pole, right, such as it existed when it formed. And so when you go through the different layers of lava flows, you develop what you call an apparent polar wander path. Well, it's not the pole that wandered, it's the continent that wandered. And he's been able to figure out that Laurentia was clipping along. During that 30 million years of magmatic activity, it went basically from the poles to the equator in that 30 million years. And he's been able to document that very precisely. So that's kind of creating a whole new way of looking at how the rift might have developed. And so that's going to be really fun to watch. And we're getting better at dating the rocks. We can date these billion-year-old rocks to an accuracy of like 500,000 years, which is pretty good. You have a 30 million year window, and you can date things to within 500,000 years.
Yeah. All right. Well, there's a few more questions here if you still have time.
Yep, I'm good.
Yeah, you recommended the maps. Are there any other apps that you would recommend for GPS tracking and geology?
Oh, yeah, I'm too old school. And there's actually, we had a North Central Geological Society of America meeting in Duluth just a couple weeks ago that was virtual. But we planned some field trips for that, and there was, of course, we couldn't run the field trips, but we had the option of uploading our guidebooks to some geo-referenced apps, right? So you can go on and say, I'm here, tell me the geology of this area. So I know they're out there. I couldn't tell you the names of them. I can't remember the exact names of them, but I know they're out there. But you know, when I was doing my work in Minnesota, it was we didn't have GPS even, right? So when you're going traipsing through the woods trying to find rock outcroppings, you basically had your compass and you knew what your pace was. So you headed for that knob that you hope is like 200 paces away, and hope that there's rock when you get there. But things like a GPS has revolutionized that process.
Let's see. Does Lake Superior have an unusually small watershed for the size of the lake? I've heard that some climate models predict that global warming could cause Lake Superior to cease to flow at its outlet and become a salt lake. Well,
yeah, that's not an area of expertise I have.
Yeah.
There's some people down in Duluth at the Large Lakes Observatory that have done all kinds of studies of the warming of the lake and so on, and the chemistry of the lake. I'd go to that area, that website that they have, the LLO. But it does have a small basin, for sure, drainage basin. It's as these things go. But it's traveling, I don't know, to become saline like that, I would think you'd need a whole lot different geology around the perimeter of it than we have today. We have very inert rocks, you know, they're just crystalline, igneous, and metamorphic rocks mainly. Not a whole lot of salt deposits or anything like that in the Lake Superior Basin.
All right. Let's see. We're getting down on the list here. Is the movement of sand by the glacial movement the primary cause of the greater depth of Lake Superior compared to Lake Michigan and other lakes?
Probably. I think the original that trough of sand that filled in between the basalts when the rift formed, that thing was 10 kilometers thick. That layer of sand, and again, if you go to Bayfield Peninsula, you can carve your initials in those sandstone outcrops with a stick. So it's very poorly cemented, and the glaciers, it was just like eating candy to them. It just ripped it right out. The basalts, much harder rock, much more resistant to erosion. So those hold up the margins, those hold up the shorelines of the lake basin. And there's still a lot of sandstone down there that wasn't fully excavated.
Okay, I think we'll get down to our last question here.
Okay.
Someone mentions they've heard there are places you can find copper around Lake Superior besides the old mines.
Sure.
Do you have any recommendations about that?
Just keep your eyes peeled. Just like agates, the glaciers picked up pieces of mass copper off the Keweenaw Peninsula, off of Isle Royal. There's a few showings on the North Shore by Knife River. And that all got transported south. So every night, wherever there's superior sourced glacial material, there's a potential that you could find a chunk of copper. Interestingly, you might have heard of the Ontonagon boulder. It was this big mass of copper that was, I think, about 5 feet across and maybe 1.5 feet thick, this lens of mass copper that was sitting on the banks of the Ontonagon River about 2 miles in from the shore. And the Ontonagon River is really deeply incised, almost canyon of a river. But the Native Americans knew all about that, and whenever you'd get like Schoolcraft or any explorer that would come through the Lake Superior Basin, they'd take them and show them this mass of copper. That triggered some entrepreneur to decide there must be a vein of copper in the hillside there. Well, the hillside of the Ontonagon River was basically all loose gravel and debris that the river deposited. And that was just a chunk of, what we call a glacial erratic. It just got picked up out of the bedrock and transported some distance and then dropped there by the glaciers. So there was no vein of copper, but he would mine into the wall of the valley, and it's all unconsolidated debris. So it kept collapsing on him. So he thought, well, I'm going to build it in the winter and everything will firm up and then I'll get in there. And so he did that and I don't know how far deep he got into the wall of the valley, but come spring, it collapsed again, and it was like there was nothing there. And then the theory of continental glaciation was actually developed in the mid 1800s, about the same time. Louis Agassiz, a Swiss naturalist. And if you ever go to Calumet, Michigan, his son, Alexander Agassiz, actually became the mine captain of the Calumet Hecla copper mining company that did most of the mining in the Calumet district in the late 1800s, early 1900s. But yeah, you can find copper, and you can find them in the rocks. You can go up the Keweenaw Peninsula and go through some of the waste piles, and you'll find little flecks of copper here and there.
All right, and I missed one question from Mickey, who I see is still here. I would like to know how Isle Royale was formed. Do you have any suggestions for reading?
Yes, there's a great book. Let me, I have it here. Oh, should have anticipated this question. I can't see it right now, but there's a book called The Geoheritage of the Lake Superior Region. It's by Bill Rose and Erica Vi. They're from Michigan Tech. And it's a nice, small, little pamphlet-sized book. You can find it on Amazon, I'm sure. And again, William Rose and Erica Vi are the authors. And it basically talks about the geology. That basically, we talked about how the Keweenaw Peninsula, all the lava flows are tilted to the north, right? And when we did this reflective imaging, the seismic imaging, we could see that between that and Isle Royale, they come right back up to the Isle Royale side, and where it's tilted to the south. And so they're all part of the same package of lava flows in this trough of lavas. In fact, the main ridge former on the Keweenaw Peninsula is called the Greenstone Flow. It's the exact same flow that holds up the backbone of Isle Royale, called the Greenstone Flow. I happen to have a student, one of my last grad students, actually compared the two flows and showed that they were in fact identical. And so it goes all the way under the lake and comes and reemerges at the surface at Isle Royale.
Okay. Well, Jim, thank you so much for doing this, and thanks to everybody who attended. I want to make sure to let y'all know that Northhouse will be doing more programs like this. Next week, the interns are taking over our Crafting in Place program, and so they will they'll be doing programming on Instagram and Facebook. And then the following week, we'll be having a Thursday night webinar on cedar strip canoe building with Ken Kosick. And then the week after that, June 15th, that whole week is our Wooden Boat Show, the digital version. And so we will have a webinar every night of the week at 7 o'clock. There are some incredible speakers coming virtually to join us. You can already register for those on our website. So there's Norwegian boat building and sailing through the Northwest Passage and the history of the Grand Marais Harbor from Stacy Drouillard, who's an Anishinaabe woman who lives in Grand Marais, and some other wonderful presentations I'm not remembering, but all of it's on our website. So please check it out and sign up if you'd like to attend those. We do hope that eventually Jim will be back in the classroom teaching in the flesh, and that you will all be able to join us when we're able to do that safely. So in the meantime, thanks so much, Jim, and thanks to everybody for attending.
Thank you, and thanks everyone. Have a good day.
Have a good weekend.
Yeah, bye.
Bye-bye.